everybody. On behalf of Photonic Israel Association, I warmly welcome all the participants. My name is Shlomo Glaser. I am the manager of Photonic Israel. This conference is organized by Vulcani Research Center, Optech Berlin-Brandenburg, and Photonic Israel. I would like to ask all the audience to switch off the camera and the microphone and switch it on when your turn comes. So I would like to ask Dr. El-Hanati to congratulate on behalf of Vulcani Research Center. Please.
Thank you, Shlomo. Good morning, everybody. I am pleased and a little bit moved to open this agriphotonics webinar. As a matter of fact, Vulcani and also the community that works on optics in agriculture has been for a long time working on cutting-edge technologies, but I think the term agriphotonics was not used so much. I used to be part of the biophotonics community, and I envied very much the photonics people and biophotonics community for being together and working on biological aspects in photonics. And now here's the opportunity of taking agriculture as the main focus and combining it with photonics. I'm sure that the community in Israel, Vulcani, and the other academic and research institutes have a lot to contribute from the agricultural and technological part. The companies in Israel and in Germany, and also the academic and research community in Germany have a lot to contribute on that. And I'm very happy to see such an event that is going to link those both together in order to get really exciting things in photonics in agriculture. So I welcome you to this webinar, and I wish you a fruitful day. Thank you.
Hello.
Shlomo, back to you.
My name is Dr. Janina.
All right. Please.
Hello. I'm from Optic BB. That means that's an association here in the capital region of Germany, Berlin-Brandenburg, dealing with optical technologies and microsystem technologies. And I have prepared some slices at the beginning. Okay. So that you can see who we are. We are founded in 2000. We are founded by companies, universities, and research institutes, and different associations. And we have been supported by our Senate and ministries from Berlin and Brandenburg. And today we have around 120 members in our community here in Berlin and Brandenburg. But we are also part of OpticNet Deutschland, who's an association of all the German regional competence networks of optical technologies with more than 500 members. We are also a member of APIC, and we are engaged in Photonics 21 and cooperating with Spectaris. Also, we have a bigger community and working together with our partners from Berlin Partner and also from the Economic Development Agency from Brandenburg. And that it's the photonic cluster from the capital region. We have a long tradition here in Germany, especially in Berlin and Brandenburg. And in the core of our cluster, we have over 400 technology-oriented companies and also around 30 universities and non-university research organizations. Our focus areas are lighting technologies, laser technologies. We are also working in photonics and quantum technologies for communication and sensors. We are working with optical analysis, microelectronic and microsystem technology. And last but not least, we have a focus area with biophotonics. And in this area, we decided to make a cooperation with our partners in Israel with Victor Alcianati and also with Photonics Israel. And we focused on agriphotonics. Our network has the goal to collect plant material, knowledge-based and locally adapted data to make a more sustainable and a more economic farming possible, and therefore we want to use photonic technologies. For the moment, all of you know that photonic technologies are already used in agriculture, but we have still some problems with limited data generation. Also, we have a lot of single sensors that are not able to get the data management together. And we have a big variability of biological samples itself, and also the costs. You don't have to forget about the costs. So the scope of our teamwork would be to focus on photonic sensors technologies. We want to improve the existing solutions. We want to make them smaller. We want to have less energy consuming, and we want to make the solutions that already exist better, like higher resolution and also cheaper. And the goal is that the farmers would be helped to make a smarter and faster and more economic crop management decision. That's our project management. On the German side, we have Optik BB, and we have the Leibniz Institute for Agriculture, Engineering and Bioeconomy. And on the Israeli side, we have Photonics Israel and the Vulcani Institute working together. Just to give you a short overview of our partners, as you can see on the left-hand side, there's all these small and medium-sized companies from Germany and Israel that already agreed to be an official partner of our SIM network. On the right-hand side, you can see a mix of German and Israeli institutions and universities. And we have also partners that help us, bigger partners, big players, and also smaller companies. What we are looking for, it's to get a bigger network, and we invite small and medium-sized companies to join us, even so the research institutes and the big players, and we all want to work together and to get a bigger expertise and knowledge in agriphotonics. So that's our contact details, and I want to close my opening words with a save the date. As you know, after the conference is before the next conference, so save the date for the next agriphotonics workshop in October. It's the 7th of October, and it's in the framework of the Photonics Days Berlin-Brandenburg. Thank you.
Thank you very much, Dr. Bolling. I would like to ask the co-chairman of Photonics Israel, Mr. Chaim Russo, to congratulate the audience. לא שומעים אותך, חיים.
Yeah. Good morning. On behalf of Photonics Israel, I'm very pleased to open this event, which deals with agriphotonics. This event is an example, another example, of a very fruitful cooperation that we have in the last 2 years between Photonics Israel and Optek BB, the cluster of photonics cluster in Berlin area. And I want to take the opportunity to thank Frank and Janina from Optek BB and Shlomo Glazer from Photonics Israel for their dedication to organize and to arrange all the things regarding this event. Photonics Israel is the organization that try to support the photonics community in Israel, both companies, industries, and academia, to expand their business. We were established about 2 years ago, and our main objective was to encourage and enhance cooperation and developing business opportunities between the Israeli community and the communities worldwide. At the time when we established Photonics Israel, we didn't understand and we didn't imagine how critical and important will be our role. Since last March, since the COVID-19 is part of our life, you know that research people, engineers, business people are not able to meet in person. Most of the conferences were canceled, and which was the way of people and companies and organizations to try to identify the cooperation. For the first month, we were in the dark, but then we decided to go into this vacuum and try to build new bridges. And what we are doing today is one part of these activities. In the last 2 or 3 months, we organized tens of webinars and events. Most of them were international participants with international people. And the event of today is one of these. You know that Israel is very well known for its excellence in agriculture research. Photonics is one of our core technological expertise. We identified something like 75 companies in the field of agriphotonics in Israel. Part of them, big part of them, I would say, are small companies, startup companies, so we can expect in the next few years to see more and more activities in this field. We believe that applied research and engineering innovation in agriphotonics are assets that our part, the Israeli part, can bring to the table. There is always the question, what makes such an event a successful one? Is it how many interesting lectures we have? How many people in the audience participate? And yes, this is important. Interesting lectures are important. Participation of many engineers, researchers is very important. But the most critical element is that by such an event, we will be able, the companies or the partners on both sides will be able to identify opportunities, and they will start some joint activities very soon. So with this respect, I wish us all a fruitful and successful day.
All right, Chaim, thank you very much. The Ministry of Agriculture Chief Scientist, Professor Gera, will speak on advanced agriculture in Israel. Professor Gera, please. לא שומעים אותך. Switch on your microphone, please. No, your microphone is still closed. Please switch it on. Okay, now.
Good morning. My name is Abed Gera. I'm the Director of the Plant Protection and Inspection Services. And since September 1st last year, I'm the acting Chief Scientist of the Ministry of Agriculture. So on behalf of the Minister of Agriculture, I wish to express my profound gratitude to the organizers, especially to Victor and Shlomo, for the privilege of addressing the agriphotonic virtual workshop as a part of cooperation between Germany and Israel. Agriculture research in Israel is carried out by the public and the private sector at the universities and research institutions. Research is primarily funded by the public sector, of which the Chief Scientist of the Ministry of Agriculture Fund provides the major share. The fund was established to advance, foster, and support research carried out by Israeli researchers at the academy and research institution. The major goals are to identify agricultural challenges and problems which knowledge gaps exist, to determine research goals aimed to bridge gaps and to fund such research activities. The majority of the funded research projects are focused on increasing agriculture productivity, particularly in hot and arid climates, plant and animal health, food quality and safety, and environmental issue. We monitor research performance in order to guarantee the implementation of the outcome for the benefit of the farmers, public values, and environment. The major subjects that are currently supported and controlled by the chief scientists are dealing with agriculture, biotechnology, animal and food production, food quality and safety, genomics, irrigation and water management, sustainable agriculture aiming to reduce the use of pesticides. The chief scientist is supporting precision agriculture through optical sensing, remote sensing, proximal optical sensing, optical systems for a quality inspection of agriculture produce, methods and algorithms of machine learning, novel optical methodologies that reveal beyond the human eye can perceive, the application of photonics technology in the field of aquaculture, water quality, and optical sensors, fish behaviors, smart feeding technology, lead lighting, early diagnosis of diseases, and adoption of photonics technology as a key element for food safety. Today, and mainly in the future, complex climate changes, demographic growth, and energy context, agricultural research must deal with the major issues on various scales to ensure food security, preparing worldwide food availability and security by 2050, and promoting alternative agricultural practices that can respond to non-reversible climate change, which are challenges that the entire world must facing. We believe that the COVID-19 pandemic has underlined the importance of a robust and resilient food system that functions in all circumstances and is capable of ensuring access to a sufficient supply of affordable food for citizens. It has also made us accurately aware of the interrelations between our health, ecosystem supply chain, consumption pattern, and planet boundaries. The current pandemic is just one example. The increasing recurrence of drought, floods, forest fires, and the new emerging pathogens and pests are constant reminders that our food system is under threat and must become more sustainable and resilient. Our strategy is oriented to address comprehensively the challenges of a sustainable food system and recognizes the links between healthy societies and a healthy planet. In the aftermath of COVID-19 pandemic and the economic downturn, a shift to a sustainable food system can bring environmental, health, and social benefits, offer economic gain, and ensure the recovery from the crisis put us onto a sustainable path. Soil and water, the natural resources that underpin agriculture production, are under continuous stress. Thousands of hectares of lands are lost from production, because of urbanization, degradation, and desertification process. Land degradation coupled with the rapid human population growth results in a significant reduction in the level of land per capita, which is available for production. Fresh water is also scarce and insecure resource. In 2050, more than half of the world population could suffer water shortage. The implication of the diminishing stocks of productive and water are severe. The impact of climate change are global in scope and exceptional in scale. In fact, in 2050, there will be about 10 billion people to feed, demanding production of more healthier and cheaper food. To do that, over the next 30 years, we will need to increase the global agricultural production by at least 70%, maintaining food production to feed a growing population during a period of climate change, while preserving the environment is one of the major challenges of our time. And without drastic actions today, adaptation to its future impacts will be much more difficult and costly tomorrow. Advances research and applied science can yield technology that would play a key role accomplish the task, while consumer-driven technologies such as mobile phones is widely pursued by science, R&D, and industry. Agricultural technologies breakthroughs are less attractive for the immediate fortune seeker, although their global importance is by far more critical. Precision farming, which is, encompasses data sciences, sensors, information, and communication technologies, as well as robotics and cyber, is one of the leading technological discipline that carries the potential to enable more sustainable agriculture. Data acquisition and sensors technologies are usually borrowed from the medical or the defense field, for which significant budgets are located for their development. Nevertheless, an in-depth understanding of the physical principles and the appropriate adjustments are essential to make them usable for precision farming. I trust that the current workshop, researchers from Israel, Germany, Denmark, the UK, and the US will share unique data about acquisition process from discrete sensors through proximal sensing to remote sensing. Various data processing algorithms are applied, and appropriate decision support framework are utilized. The vast diversity of the topics in this workshop reflects the wide scope which photonics technology can potentially increase farming efficiency and support sustainable agriculture. In the last few years, we are witnessing a dramatic increase of new agriculture startups, companies in Israel. The majority of these companies are dealing with precision agriculture technology, such as artificial intelligence, robotics, drones, satellites, sensors, algorithms, etc. Israel's leadership in agriculture, innovation, and technology has introduced time and a cutting-edge solution that address global challenges. Our goal is to support this emerging industry and help more new technologies to successfully overcome the valley of death on the way to the market. Since 2018, we initiated a new track together with the Israeli Innovation Authority, the agriculture track, when the state participation is 30 to 60% of the eligible cost. Within the framework of this track, applications of 3 different types were applicable. R&D grant to companies, cooperation between regional R&D centers and company, and installation of new products at the customer sites overseas. In conclusion, research and innovation are key drivers in accelerating the transition to sustainable, healthy, and inclusive food systems from primary production to consumptions. Research and innovation can help develop and test solutions, overcome barriers, and uncover new market opportunities. With the Chief Scientist Office, we are planning to prepare a call for proposals on food, bioeconomy, natural resources, agriculture, aquaculture, and the environment, as well as the use of digital technologies and nature-based solution for agri-food. A key area of research will relate to microbiome, food from the sea, urban food systems, as well as increasing the availability and a source of alternative proteins, such as plant, microbial, marine, and insect-based protein and meat substitutes. A mission in the area of soil health and food will aim to develop a solution for restoring soil health and functions. We believe that new knowledge and innovations will also scale up agroecological approaches and primary production through a dedicated partnership on agroecology living laboratories. This will contribute to reducing the use of pesticides, fertilizers, and antimicrobials. To speed up innovation and accelerate knowledge transfer on behalf of the Ministry of Agriculture, I wish you a successful and enjoyable meeting with a lot of good sense and some fun. Thank you very much.
Thank you very much, Professor Gera. The Vulcani Research Center Associate Director for Academic Affairs, Professor Alstein, will speak on the advanced agriculture in Vulcani Research Center. Please.
Just 1 second. Okay, thank you very, very much for the invitation. I would really like to congratulate Optech BB and Photonics Israel for taking the initiative and organizing this very important and interesting forum, and for inviting the Vulcani Center to be part of it. I would like very briefly to introduce to you the Vulcani Center. So the Vulcani Center is celebrating 100 years next year. It was established in 1921, and it turned to be the research arm of the Ministry of Agriculture in 1956. Currently, the Agricultural Research Organization, or Vulcani Center as it is called after the person who established it, Dr. Elazar Vilikansky, Vulcani, is currently the largest agricultural research institute covering the vast majority of agricultural research in Israel. 3 years ago, we were acknowledged as a very important center in the field of life sciences by UNESCO. We were awarded with a very prestigious prize for an institute that leads or led to an improvement of the quality of human life. In terms of the structure of the Vulcani Institute, we constitute of 6 institutes and 2 research centers. And the various institutes and research centers cover most of the issues that are dealt by agricultural and environmental sciences. And those are a post-harvest and food science institute, soil and water institute, animal science institute, plant protection, plant sciences, agricultural engineering, and 2 research centers, one in the north, Neve Yaar, which focuses on health food, and one in the south, which is called Gilat, and focuses on research aiming to solve problems of agriculture at the edge of the desert. On top of the different institutes that cover the topics I just mentioned, we also have several virtual interinstitutional centers which focus on implementation of agro-technological methods in the different topics studied at Vulcani: genome editing, medicinal cannabis. The Vulcani Center has been announced as the National Center for Medicinal Cannabis Research. We have an omics center which integrates scientists that specialize in bioinformatics, proteomics, and metabolomics, and a virtual center for microbiology, which focuses on the importance of microbial factors in environmental, plant, animal, and food sciences. Vulcani Institute is not a large institute. It consists of 190 scientists, of course, research assistants, administrators, but despite the fact that we are not a university and we do not award degrees, we do have around 250 to 300, depending on the year, of graduate students who are enrolled in universities and come to do their research projects and research towards getting the 2nd or 3rd degree at the Vulcani Institute. And this is managed by agreements that we sign, that we have with all universities and research institutes in Israel. We also have special agreements with some countries like India, China, and Japan, within the frame of which we train foreign postdoctoral young scientists. And we also have postdocs that come on their own without any agreement from different countries around the world to do their postdoctoral training at Vulcani. And we also have, of course, Israeli postdocs. All in all, we have around 1,200 employees and volunteers. The scientific ID of the Vulcani can be described by the following topics. The research spans all the way from very basic to applied research. One very important and main characteristics of this research at Vulcani is its multidisciplinary research. As I mentioned, we have 6 institutes that focus on different aspects of agricultural and environmental studies, and it is very easy to establish multidisciplinary research group to try and focus on emerging problems or on important issues based on needs. All studies at the Vulcani Center integrate cutting-edge technologies. We have a lot of collaborations with academia, national and international, within the frame of national and binational or multinational research grants. We have regional cooperation. We have cooperation with regional countries, again within the frame of a research fund provided by the US, which is called MERC, Middle Eastern Regional Cooperation. And very important, which are the collaborations with the extension services, with the research and development regional centers in Israel. We have 8 such centers that spread throughout the country and focus on regional issues that are important for specific regions, and with farmers. And this is very unique for the ARO. Those collaborations focus on the real problems as are raised and brought from the field to the scientists at Vulcani. The research at Vulcani is carried out based on a strategic plan which covers agricultural, environmental, and food sciences. This strategic plan was established several years ago by people from the academia, not only from Vulcani, but from Israeli academia, by policymakers, of course, Ministry of Agriculture, commercial companies, etc., etc. And it is evaluated every 3 years to see. Pardon?
People should close their microphones, please. It's disturbing.
Okay, so this is as far as the strategic plan covers, and since we are a governmental research institute, we focus on issues that are national challenges for agriculture, such as competitive markets. Israel needs to be highly competitive, and this is dealt by development of unique varieties of fruits and vegetables that can be sent to markets abroad. Efficient water management is another very important topic. Israel suffers from lack of water, and efficient water management is a very important issue. Labor cost is very high in Israel, and we do need to find solutions to solve the high labor cost. And landscape preservation. Over 50% of the land of Israel, which is small anyway, is a dry land, desert land, which is not adequate for agricultural development. And we need to preserve the very small amount of land, the very short amount of land that we have for agricultural development. We also, of course, focus on global challenges, which also cause a problem in Israel. And those are global climate changes and climate adaptations. We're trying to find solutions to adapt to the climate changes. Food security that Professor Gera mentioned in his presentation, food safety, free of toxic chemicals, free of pesticides, and all of the above while keeping the environment sustainable. ARO integrates photonic technologies in a large number of projects that I mentioned within the scope of the challenges that ARO focuses on. Currently, we have 22 groups from different institutes that focus on different projects such as precision agriculture, machine learning, computer vision and imaging, and remote and proximal sensing and diagnostics, ripening and sorting, infestation and food losses, crop improvement, weed management, phenotyping, trying to manage biotic and abiotic stress, irrigation, determining irrigation status, decision support systems, air and water quality, soil-plant interaction, plant nutrition status and biomass, microbial food safety, etc., etc. And Dr. Iftach Klap, who will follow my presentation, will elaborate on the agriphotonic activity at the ARO soon. ARO has also a technology transfer unit. Many of the projects have a commercial potential, and this unit, which is called Kidum, manages our commercialization and related activities. They evaluate and try to determine the feasibility, the commercial feasibility of the studies. They take care of IP protection by patent filing. They try to get money, pre-seed investments in order to prove concepts of different projects. And they license rights of to different companies and try to establish joint ARO industry R&D projects. So to summarize, what we focus at the ARO, or what we aim at the ARO, is to be able to allocate the needs in the field of agriculture and environment in Israel and globally, to try and find innovative solutions for those problems. The close collaboration with farmers, extension services, and regional R&D centers enables us to do local testings. And then, of course, we are aiming to globally scale up those projects and develop technologies, machines, varieties, compounds, etc., etc. I thank you very, very much for your attention. And I really wish everybody a very interesting and productive meeting.
Professor Alstein, thank you very much. The Vulcani Research Center scientist, Dr. Iftach Klap, will speak on the optical acquisition challenges in agriculture data mining. Iftach, please.
Okay. Good morning, everybody. You see me? Am I hearing well, Shlomo?
Very well.
Okay. So thank you very much for this. Would like to thank the organizer for this meeting and also for this opportunity. I'm giving now the first lecture. It will be followed by many other works done here in Vulcani and in other academia in Israel. Very interesting, I'm sure. Today I would like to discuss shortly cross issues associated with optical acquisition and how it's cross issues with the data mining. So agriculture, I mean, typically what we have in front is very large field of view. Our inspection is of the size of many tens of actors, typically in Israel, and also worldwide more than that. So our main tool is remote sensing devices. And we would like to have very good information, so very high quality information. So we need for very high level sensor, which are typically very expensive. So as long as academic research is done, researchers can purchase themselves very high quality systems. But when it comes to agriculture implementation, we need for a low cost solution. And that poses a problem because what we are after is data mining. That means to get information out of what we sense. And when the acquisition systems are limited by the budget, we have a cross issues, and these cross issues make a huge challenge on the optics research. So this is Ariela, one of my former colleagues. We did a lot of work on cotton inspection, and the question at that time was that we were subjected to new bug, molybug, that was ruining the cotton in Israel, and the question was how to find something very small in the field. So on the top, I mean, in this slide, you see now, this is the cotton field from, on the left, from about 100 meters top.
Iftach, we cannot see your presentation.
You don't see my presentation?
You need to share it on the screen.
Oh, this is what I, pardon, share screen. I thought it. Thank you for telling me. Now you can see it?
Yes.
Okay, beg your pardon. Okay. So, I would like to go one slide before it's important, and then I will go on. Well, the situation in inspection of a field is that the man is very small, need to find something in a very large field of view. So these are images, typical images of cotton field, which looks like huge, tens of dunams of continuous rug. On the right, I present here what you see, this very large spot, a black spot. It's what left after the molybug damage in Israel. This is of the size, can be of the size of football yard. And in Australia and in India, this particular molybug damaged 30% of the cotton. The issue is that when you got this, you already, the bug is already spread all over the field, and you need to find it where it's still in its initiate stage. But as you can see, the bug on the left in figure A is very small one. I mean, it's few millimeter bug, and we cannot really, I mean, inspect the entire field, I mean, to look for this. So we need to go and to do a remote sensing, and then we get this on the right, which is the clusters of the bug. And now we would like to make some sort of data mining around that. That means a classification, a machine learning pattern. And one part of it is to classify it by color. On the right, what I present here is the bug in, I mean, a zoom in of a bug. And what you can see is that the bug is when it's close to a brown leaves, it looks like brownish on the bottom left. And on the top left, it is look like very much on its outskirts green, because of it's standing on a leaf, and when it's in a shadow place, it's look like in gray. So what is the color of the bug? I mean, how can we make a description, right description for this? The question is, I mean, can be answered if you plug in optical information. On the left, I present a target, I mean, a resolution target from a typical distance. And what you can see that this become blurred, and we all know this blur, but when the target is very small, this blur causing of a mixed pixels, and that is a penetrating in information from the background. So if in this work, what we suggest that if we measure the information, color information in the environment of the bug, we can know the physical information of the point spread function of the system. We can plug it in the information. So what's going on? To do that, we need to understand what's going on with the histogram, this information, the spatial information. And what we can show that the overall histogram is a summation of the local histograms. And then what we suggest is to take the information of the expected color of the bug and convolve it with the point spread function, and only afterwards making a decision regarding the existence of the bug or not. So after implement that in a simple decision support system, we could go to a cotton field and find suspected places. Some of them aren't current. However, you can see that we can actually find a very little amount of false positive and find bugs in places that looks very healthy before the bugs ruin it. And here is another example. In a deep field, we can actually be specified only a few places There are indeed suspected as a bug. In some places, we have problems with the cotton flower, but this can remove with forward, a more detailed investigation. Going on with other challenge, we have, as I say, we are always limited to the budget. So on the top, I presented here, a spectra, typical spectra measured by RAMP and the company of sugar beet leaves, which are subjected to some pathogens. And as you can see, they have found that it is very known that we can use spectroscopy to identify chemical changes in the canopy. However, we are looking for a field, so on the right, so we need a hyperspectral imagery in order to really inspect the entire field. And in a specific work, we would like to make a design for a system, a scanning system that can work from a tractor. That means it should be robust and of course should be low cost. So what we suggest here is to use two-way scanners, which works very well with LiDAR system. However, in LiDAR system, we are dealing with a monochromatic system. So the dispersion nature of this prism is not a really hard issue. But here we want to make an hyperspectral system, so the dispersion is very strong. So we built this system, and this system is composed from two scanners, two prism scanners, a collimated system attached to a point spectrometer, which are much lower in cost than a hyperspectral system, and a review camera, which allow us to make registration between different point of view. And then we had to really analyze what's going on in the system. So what's going on in the system, this is a point spread function of the simulation. We modeled the system, and this is what's going on with the system. The point spread function, this IFOV, the specific IFOV of each point, is changing its size as we going out to a remote field point. In addition, the size of the color, each point sees different field of view for each color. So the color collection is biased by the collection and also is shifted when we go out. What you see on the bottom is validation that we actually make an inverse of the colors and put plugged in colored illumination and show what is already seen in the present, what already seen in the analysis. Now, the system, the analysis also will help us to know what we can expect from the prediction of the system. The above is the simulation after taking all the optical properties of the system, and below it's the results of the scanner. In the real world, in the real experiment. So what we did, we placed we could place this system, this scanner on the post and make a scanning for here from on the top, on the bottom left of wheat field, for example. The way this system also suggests us to in the end of it, for every field point or for every image, we have actual full cube of hyperspectral, so it serves its purpose. Now, what can we do with the aberration? So above, it's first in simulation. We have, because of the spreading of the colors, we have this unbalance. It's supposed to be black and white checker box, and where the blue and all colors are equal, so it's supposed to be black and white strictly. And after we use our algorithm supported by the model, we could make first a correction of the reflection, which is also including the size of the point spread function, left with the registration issues in the outskirts, and we can also correct for that. Below, it's a experiment. So first, we make a white balance. Because this is not completely white, because the component in the real world are not exactly red equal blue and green. Now we left again with only the errors in the outskirts, and we also was able to correct them with the proposed algorithm. So eventually we had a system that is more or less see the specific target spectral without too much influence of the its location in the field of view. So we could be happy that we can actually scan as the system with a dispersive scanner. Going on with that, I would like to present shortly something I gave. There is a full webinar on that. We were after low-cost thermography. In agriculture, we are very much after using low-cost thermal cameras for the sake of measuring canopy temperature, which reflects many important biological issues, and of course irrigation. There are two challenges with the low cost, about 2,000 euro cameras. First, that we need to be within very narrow range of temperature. I mean, very accurate to actually distinct between problems in the canopy to a place that there is no issues, and also that the number of pixels is very small relative to RGB, and so we have all these mixed pixels. You can see on the right that the pixels of the canopy near the path becoming with a different color. Although I mean, you see it also on the top of the canopy. Only the camera is taking information from the path after the canopy and mix it with the information of the canopy, and we get, in the end of it, we get wrong temperature estimation. So here we have to deal with modeling what's going on to take in consideration the optical formation. I mean, all this parasite information on the right in red, which is mixed with the information coming from the actual measurement. What you see on the bottom right is measurement did by Teppelman and his colleagues after 2-point correction. This is what we left with, and it is unknown because this additional information coming from unknown temperature or thermodynamic state. So what we suggest is that we can make double measurement by adding more information. This is the image formation equation, and we can just very quickly change the point spread function identity by defocus, and then we have additional information, and by taking images for more than 1, 2 and more images, we can have sufficient information to solve a blind deconvolution algorithm that we suggest. And the results are that if you see now, there's a pairs of focused and defocused images, and there are also have this shady around it, the shady pattern, which is associated with this parasite unknown information. And what we get in the result, that very accurate information about, I mean, this is in on the third line is the results, and below it, it's the ground truth. So, and it's very accurate. Another issue is the issue of resolution, as I say. So in another project, we suggest how to make a super resolution for a low-cost camera. Works very well for the Opgal thermop, and we also try to take it out for other cameras. For instance, this is original images taken of plant in proximity, and you see there's an initiate of growing, which is covered by all this noise. And after we learn the noise and learn the way the system behaves, I mean, in the aspect of resolution, we can make this on the right, this restoration, and getting much more information for the farmer and the breeder. Finally, I would like to show two simulations that mimics the entire concept. Here, what I see present is the mosaic image of system that's subject to some sort of error, like you I present previously, and make a mosaic so we see all these boundaries because of the difference in mosaic in the gain and offset that change in this camera. And also it has a natural resolution which is not that high, and so we get this, and we have a RMSE error of 8.2, which is larger than the entire range of temperature we would like to measure. However, when we correct the system and improve the resolution, we get that with RMSE of less than 1 centigrade, and this is what we really after. So we hope to achieve that. Before I will end, I ask for the permission, together with from the organizer, together with other colleagues. We are now presenting or trying to organize a special issue about these cross issues between algorithms and optics. So if you have good work, sufficient work for that, we will be very pleased to get them. And I would like to thank you all.
Dr. Clapp, thank you very much. You were right on the time. The Leibniz Institute for Agricultural Engineering and Bioeconomy scientist, Professor Manuela Zude-Sasse, will speak on the digitization in horticulture. Professor Zude, please.
Thank you very much. Actually, I'm very much grateful that we are for our host here, Shlomo Glaser, and also Victor Alchanades, who is a little bit our counterpart from ARO. I would like to give some ideas on how we could work together. I just need to make the screen shared, which seems to be a little bit difficult. I don't know why exactly. So can you see my screen already?
Yes, we see it very well.
You see it very well. Actually, I don't see it. Now it comes. Okay. Yeah, digitization in horticulture. So we are moving a little bit now in the specialty crops. And our idea is to be similarly precise as we know it from precision agriculture, where the idea came up that the plant should give us the idea of how to really manage the field or the orchard. So finally, the yield speaks to us, and we think this is economically viable. And moreover, we can avoid errors that we would do otherwise. So the community who is now dealing with precision horticulture is obviously the horticulturists, the plant physiologists dealing with applied plant physiology. We have few investors, and some of the precision agriculture community came over. And we do have the sensor community already. So as Dr. Bolling mentioned earlier, so we had different projects already to bring different sensors into the field. But from my understanding, it wasn't as successful as it could be. So I think we should really work closer together. And we need to keep in mind, so what was said before also, if we talk about plant sensors, and I hope industry is, a lot of participants from the industry are listening, we need to have it really robust, and we need to have it really inexpensive. So this is a challenge in agriculture. So we can do a lot actually already in plant sensing on different scales, but then I'm coming from spectroscopy mainly, and I find always that the spectra of an apple, they just look beautiful. But most people don't follow me in this opinion. So most people just think they are only spectra. They don't contain any information. Obviously, there are information, but I think we really need to translate it to the grower. And for that we need the physiological model. Yeah, so I think, again, we need to work together, industry and research, the plant physiologists and the hardware designers, and we cannot forget the software, obviously. Finally, we need to bring that all into the agricultural process. So now we are going into this dark green area, and here we even need to talk to the grower, how they would like to have the result. Would they like, if you talk about irrigation, would they like to have it machine to machine so that we open and close the valve for the irrigation pipe? Or would they much prefer to have an information on their mobile phone to get to know, okay, so now I should go into this and that field and give a little bit more water or less? So we need to talk to them in this stage as well, and finding really a group to go forward to finally have these ICT solutions that we would like to have. So I would like to show a little bit more on how to measure into an orchard this time. So how can we bring the sensors into the orchard? And obviously we can use established machinery. So we can use tractors to bring in a leader, to bring in camera systems. That is doable. We need to make sure that the tractor is available, because tractors are always scarce somehow, so they are used in many processes. So in horticulture, we go something like 35 times around into the orchard to do some measures. So we are going often there, also with a tractor, but it is in use quite often as well. So it might not be available at the time where we need the data. So we can go for autonomous platforms, and so there are a lot available right now. This picture is from an European project that we had some time ago, and then the platforms were only in the initial stages, but now we have many platforms actually that are out in the field already. When we go to the bigger farms in Germany, they do have the autonomous platforms that are moving autonomously, satellite driven, so available. However, as we see on this image, sometimes they need maintenance. And then I think we also need a very sound business model, how to keep those machines. And it starts with a platform, but it ends definitely with a sensor. How to keep them running, really, how to maintain them into the field. So one option, probably certain for sure, is that we are only selling the service. So the system, the sensor, the platform, it stays with the company, and only the service is sold. That has many advantages actually. So because of calibration, data reliability, it all remains with a manufacturer or with the owner of the system. There are also disadvantages because then we cannot sell the hardware. So, but we need to probably decide case by case. So we do have the drones, the unmanned aerial vehicles, for example, for measuring RGB images or measuring thermal images. And definitely we need more thermal cameras, and we need cheap ones. I will come back to that later. Wireless sensor network, for me, is still a very good option. This is on the picture below. We see how it looks like when we do a measuring campaign. So colleagues are out and we are doing different measurements there. And then we do have sensors directly on the plant. And once we go home, they are continuously measuring. And that is crucial as well, because sometimes we not only need data every day, sometimes we may even need them every hour for some processes. So then wireless sensor networks might be an option. So kind of concluding here, we do have sensors available in all scales. So we can measure directly on the crop. So like here on the apple, we can measure on the whole plant. We can do measurements with a tractor, or we can go up into the air and get a better overview to do spatial analysis. So the question how we do that, and I think this is really crucial if we want to bring that into the farm, because we need to think, okay, we have the sensor, but how to do the measurement on a daily basis then? And we always need to think about the necessity for special temporal resolution. So in some processes, like for example irrigation, we definitely need daily data. But the special resolution, that is not so necessary to have that on a centimeter range. We can also go for meters or even higher. If we stay a little bit with this irrigation to make it more concrete, so this is a typical soil in Brandenburg where our growers are situated. We do have a mixture of clay and sand, and what we see here right in the middle in red is a cluster of sand, and obviously it has different irrigation needs there because the water holding capacity is much lower than in the surrounding area. And the trees on those soils, they grow completely different than other trees. So we need to compensate the water in the sandy areas somehow. So we may not even work field-wise. We may have to work group-wise at least, or in some cases even tree-wise, plant-wise. So, okay, but let's stay with the spatial resolution. So here on the soil, we definitely need medium resolution. I mean, we cannot have a dripper for each tree at the moment. So, but we need it in a medium scale. For the time frame, we need very low temporal resolution because the soil is not changing too much, so it would be enough. So if we have a time series of something like 3 years, the pattern always stays more or less the same. So here we have a very low need for the resolution. If we get the weather data involved, and this is what definitely is necessary when we want to do a proper water balancing, we need to have a weather station. And those data normally have a very low spatial resolution. So we have it in one orchard, and we even use it for many orchards in the neighborhood. Yeah, but we need a very high temporal resolution because we need the temperature, the relative humidity, the precipitation, the global radiation. We need on an hourly basis. So that means we have somehow to bring together data which come with on a different time scale to really implement them into the model. And what I always call precision horticulture means if we want to be precise, we need also to measure on the plant. Yeah, otherwise it cannot be precise because the plant, each cultivar is responding differently to the environment. So in my opinion, we can never be very precise if we don't take into account the plant. So what we did here is with a LiDAR sensor, we were measuring the leaf area and we were measuring the crop itself. So the leaf area is interesting in irrigation terms to measure the water interception directly from the leaves that is not taken up. So that goes into the water balancing as one variable. And also the size of the fruit, what we can see on the right. The size of the fruit is interesting because from the fruit developmental stages, we can also derive certain periods of during fruit development where the fruit may need less water than in others. So for example, an apple, we do have a period of cell division where we cannot spare any water. We really need to provide enough water, otherwise the fruit won't grow because they are not going into cell division. Later on, we can go back a little bit with the water supply. That is for pip fruit. It's the same for stone fruit. So for example, this is a mobile app that we developed to measure with a camera of the mobile app to measure the fruit size in sweet cherry. In sweet cherry, we do have a typical growth rate. It starts with a very big peak, so the fruit after pollination, the fruit is growing, but then it kind of stops. So this is a period when the stone hardening takes place. But in this stone hardening period, you can easily reduce the water supply. Yeah, so you can really spare some water. This is somehow here. Maybe you would like to download the app. It's free in Google Play Store for Android. and you will see the growth curves. And then when it comes to this, so here's stone hardening, we can reduce the water, but then again, the flesh is growing, the mesocarp is growing, what we will eat. So that is the yield. So we need to supply water again to make that a little bit bigger to have the economic success. Yeah, and according to the different growth stages, we can set the so-called KC value, which is one variable, into the water balancing. So if we get closer and closer to the plant, we can get more precise and do whatever is necessary to spare the resources, and water is definitely a scarce resource, but also to enable us to even sustainably intensifying our yield, because we need that for economic success and to providing healthy food. Second example is, and we come back, as I said, to the thermal imaging. We definitely need less expensive camera systems here, because with the global warming, all problems will come. We already see that we do have sunburn in apple, we have it in citrus fruit, and what we see with kind of handheld systems, spectrophotometers, we can measure that non-destructively. But what we need is, so this is for measuring the injury, but we need it before actually. We need to see the spatial resolution of the surfaces in the canopies. So, and for doing that, we need new models and we need to have new, inexpensive, robust sensors out. Always together, so it's a hardware development together with a physiological model. What we did here with the spectroscopy was, this is a typical spectrum of the chlorophylls that we find into the fruit. So it's not only one chlorophyll. Chlorophyll is so important. So we need it for photosynthesis. It's very indicative during fruit ripening to give us the different stages, to give us a rate of ripening. And also here, when the fruit get into stress, the chlorophyll pool changes. So we have these different chlorophylls into this one peak here, and I like to work on this because silicon, if we work silicon based, this is easily measured here into this region. So we have the chlorophyll A, chlorophyll B, pheophytin A, and many more. Particularly pheophytin A is very interesting because when we are measuring, so here it's just one example. So here we had a control, all fruit had the same temperature. And then here we gave a little bit more temperature on those fruit. And here we even increased the temperature above 50 degrees Celsius. And what we saw is that the pheophytin A within this entire chlorophyll pool was increasing tremendously. So that can be measured. It's doable with hyperspectral imaging, with or measuring with these handheld devices on a local spot. Technically, it's all done. Methodologically, so that we know what we would like to measure, how to process the data, it's all done. But do we see it into practice? No. So we really need to work together with the industry. We can use, so it's, well, there is one example where we commercialize it. So for example, for measuring the chlorophyll decrease and especially the rate, so measuring time series directly on the fruit. So here you see this backpack system that is on the fruit, and we see the normalized difference vegetation index, which is focusing on the chlorophyll content of the fruit. And we see that it is quite well correlated what we are measuring non-destructively with what we can measure after extraction into the laboratory. So let's say with this kind of small backpack instrument, we can get the chlorophyll degradation rate, which tells us something about the optimum harvest date. So that is available also with a mobile app.
how do we solve this dilemma? Agrowing developed a smart imagery method of remote and close sensing, bridging over this huge gap without compromising the scanning of the entire field. Now let's see how it works. First, a high altitude UAV scans the entire field, high altitude, producing high resolution detailed NDVI map according to the survey's parameters. The map is processed and normal and outlying areas are defined. In this case, we can see 3 outlying areas. A drone is sent to sample these areas from a close distance, as maybe as 3 meters, and the high resolution imagery, in this case about 0.5 millimeter per pixel, gives all the tools that we need in order to do AI analysis for definite and trustworthy detection of pest diseases and nutrient deficiencies. Now, it seems like a very simple process. So how come this is not the common practice that everybody is doing? The reason is very simple. The market is cluttered with multispectral toys, what we call, of very low resolution, whether 1.2 megapixels per band or 3 megapixels per band in the best case, like the Microsense Altum. But the lenses, the distance between the lenses do not allow them to take imagery from a close distance. However, Agrowing designed its sensors with a remote and close concept in mind. When we look at our sensors, the lenses are adjacent to each other, where they're capturing the imagery by wide dynamic range single sensor and a single mechanical shutter. They're not multi-camera based. We enable acquiring imagery even from 2 meters and aligning the fields at the different bands without any parallax, chroma aberration, and synchronization issues. Our basic 4 bands sensor is a sensor with high quality optics of 25 millimeters focal depth. It allows us to offer high-end yet affordable 8 and 10 megapixels per band solutions. Our award-winning, we got an award at the Commercial UAV Expo last year of 10 bands. Allows you capturing multispectral data at 12 megapixels per band. And our new sextuple lens with 14 bands, narrow bands of between 20 to 30 nanometer each band, allows us to capture 14 bands of 8 megapixels each based on the Sony Alpha 7 R4. The radiometric calibration of our sensors were designed with the Rochester Institute of Technology, and the alignment was tested by Sao Paulo University. Professor Tomaselli verified that the quality is absolutely perfect. Now, based on our sensors, we have established the first multispectral imagery bank collecting samples of pathogen symptoms and pests, and we developed the first AI algorithms which prove the efficiency and robustness of the technologies. And the integration is rather smooth. We are working closely with Unique. You can see the Unique H520. On the right, on this picture, you can see our integration with the Matrice DJI's Matrice 600. We're working closely with Aplanix that integrated our sensors with their board, and Regal is using these sensors now. We had this lecture by Citri earlier today, and Citri was talking about the high resolution multispectral imagery that they are using. All the sensors that Citri is using is Agrowing sensors. So the payloads are easily integrated into different kinds of drones using also the Gramsci gimbals. And we support with our software, we allow you to have all the pre-processing, alignment of bands, radiometric calibration. We allow you to use all kinds of agricultural metrics. We support them, and we allow the users to customize the palettes and add algorithms to the software. And we also have batch conversion that allows you to take full directories in order to process them later with whether this is Pix4D or Agisoft or any other software, photogrammetric software off the shelf. We have quite a few customers and partners. Some of them were presenting today, like Migal, and citry, and we'll be happy if you looked at our website, agroing.com, and if we found that there is a place for collaboration, we'll be happy to add you to our list of customers and partners, of course. We are looking, of course, to cooperate with research institutes. We present our products with significant reductions in price to academic institutions. We're working closely these days with the Technion and others, and we'll be happy to see you joining the party. Thank you.
All right, Mr. Dvir, thank you very much. And the Mike Kropp, co-founder and chief scientist, Mr. Asaf Gavish, will speak on visible diagnostics tools for precision agriculture. Please. Mr. Dvir, you shall...
Oh, I'm still sharing the screen.
Yeah.
Sorry. Oh, share, stop share, how do you do it? Oh, stop video, stop share.
Okay.
Okay, thank you, sorry.
Asaf, please.
Yes. A sec. Can you see my presentation?
Almost, now yes.
Okay. So, hi everyone. Thanks for having me here. It's been really interesting. My name is Asaf Gavish. I'm chief scientist of a startup called Microps, and we do vision for horticulture. As most of you probably agree, precision farming is mainly based on vision diagnostics. Sensors are just not enough. And as many talks have shown here, it's helping in plant health detection, nutrition imbalances, irrigation control loops, and harvest optimization problems. However, unlike many of the talks here, in high-value crops, which are grown under roofs, aerial imaging is unavailable. So a lot of the tools that we spoke of today, like satellites and even drones, are not available to use. So greenhouse farmers are losing a lot of money due to problems that may have been solved to some extent in open fields. And between 40 to 60% of annual losses are incurred because of that. Many of them main three problems are pests problems, and temperatures and nutrients. And vision diagnostics on the whole is still being done by humans. And Microps is here to provide single plant level vision diagnostics for indoor crops. Basically, we developed a digital agronomist with a 24/7 single plant monitoring system that's based on deep learning algorithms. It's a three-part system. The user gets cameras installed in the facility. They get a dashboard to see the reports and insights, and they get an application for alerts. So they get cultivation alerts. They get suggestions for treatments and products. So it's a decision support system, and they're priced like a software. It's software as a service, monthly subscription. So let's take a step back and talk about the pillars of our product. So when we, from the onset, we had to think about how we are designing the product and what compromises we have to do to get to market. So one thing we wanted to do is to monitor all plants. We decided that it's not enough to do a subsample like the previous speaker talked about, Ira. Another thing is that it has to be cost effective. And we understood that we need to use the most up-to-date tools of machine learning. So we have to have leadership through data. So we decided to, because multispectral, hyperspectral imaging is still not cost effective, and it's not possible to spread it out in the entire field on all the plants, we had to go and use only the visible light. And this is unlike many of the talks that we have today. So I'll just take a minute to to try to convince you why visible light is the right compromise to do here. So if we take an analogy from Tesla, so all the other autonomous car companies use LiDAR, as some of the researchers speak about here. And LiDAR is very good for very precise distance estimation. But what Elon Musk here, the CEO, he called LiDAR as a crutch. And Andrei Karpathy, the chief vision scientist, he said nicely that when we drive, and humans drive much better than current cars, we don't shoot lasers out of our eyes. We just use the visible spectrum. And this is what they did. And their actual methodology was to only use cameras, but to send them into the field in millions. And this strategy has been very successful. And the idea is to lead through data. We believe as well that if the agronomist, if you had a chance to put an agronomist on each and every plant, it would already be a huge step forward. And even if this agronomist only sees invisible light, the problem here is acquisition, not wavelength. So this is our methodology. So we understood that we need to collect a lot of data. And this is why our product generation strategy started with a mobile imaging product that I'll speak about now. And then the product that we are now with installed cameras. And later on is to provide API or the actual algorithms to other software manufacturers. So the first product started with the cannabis industry being such a fast-growing and technology-open industry. And we produced the high-grade brand, which is an application that today has over 200,000 users, which are farm owners and operators. We have images from over 2,000 unique strains in variable lighting condition, angles, optical sensors, etc., growing conditions. We analyze, our algorithms analyze over 100,000 images monthly, and we are category leaders in this fast-growing market. And most importantly, the users provide us with the important data that we can take and shape into the new industrial customers. So these are actual images from our customers which fit the data that we need to go to the industrial customers. So now currently we have two pilots. One is already finished in Canada, but we have now one in Israel and now in installation one in the States. This is the largest cannabis farm in Israel. We use the existing infrastructure. As I said, we want to be cost effective and frictionless. And we use PTZ cameras, which means they're motorized and we can put less cameras in the field. This is, for example, an area that is under photography. And the idea is to have minimal hardware, but maximal coverage. And we cover each and every plant. This is an example of an image. And you can see here a magnification of a problematic zone with thrips bite, which is a very problematic pest for this industry. And we actually have sub-millimeter resolution for all the area in the farm. And just to speak 1 minute about our machine learning training program. So how do we take the images that we took from the users and turn them into algorithms? So for example, here we have a disease on leaves. We do annotation with hand annotation with professional agronomists. And then this is a creation of a mask, of a segmentation mask. We do a pre-processing that consists of quality control, some resizing, some augmentation. Then we do a deep learning pipeline. For this instance, it's semantic segmentation, but we also have object detection tasks. We sometimes do ensembles. We do machine learning on the thresholding. We sometimes use active learning. And of course, we do quality control and we use several accuracy metrics depending on the problem. Then after we have a successful system, we do a productization of it, which means to make it more efficient and to increase the inference times, like increase the speed of inference. And then we implement it and connect it with the backend and the front end and the entire system. So just an example of the algorithms. This is two images, two pairs of images. On the left-hand side, you have images that the algorithms never saw before. And on the right-hand side, you have the masks that the algorithm generated, and you can see it detected the pests and the nutrient imbalances. And this is based on users' images and implemented on larger growers. And just to finish up, as they said also in a talk just before us, it's very important to have a user-friendly interface. Otherwise, you don't get to talk to the customer. So we have this app that does the alerts and connection with the grower. And we have the dashboard that gives the actual reports and the decision support system. And today our pilot in Israel is really eating out of our hands and really enjoying the system and the recommendations that we give. And just to finish up, the next high value crops that we move on beyond cannabis is ornamentals and then leafy greens. And the reason we're here today is to ask for collaborations, to look for collaborations between researchers in machine vision, in plant sensing. And today after I saw interesting companies developing really interesting low cost hyperspectral, multispectral sensors. This is also something we would love to use, and to get in contact with grants providers, and of course investors, as we are now currently raising a seed round. So it's been really fun and interesting to listen to all the talks. And if you have questions, feel free to email me to this email, asaf.g@microsoft.ag. And thank you very much.
Asaf, thank you very much. Agro drones will not show, so we go to UGT representative, Dr. Christian Hert, that he will speak on modern research in lysometer and ecotrons in a changing world. Please.
Hello, can you see me?
Yes, we can see you, but you shall present your...
Yeah. I hope you can see my screen.
Yes,
now.
we can see it.
Okay, perfect. Yes, my name is Christian Hert. I want to introduce me. I'm from UGT. We are a German company with approximately 50 employees, scientists, engineers, and techniques. We are working at 2 locations. One location is in Münchenberg, near Berlin, where our production center is also located. You can see a photo here. The other location is Munich, where I'm sitting at the moment. We are more from the, how should I say, from the user side. So we are installing measurement points, measurement tools in the field for our customers. For example, for agriculture, water management, mining, forestry, landfills. Today, I want to focus on our lysometer and ecotron technologies. So first of all, what is a lysometer? At the end, it's very simple. You have a soil column, which is installed inside the soil on a weighing platform on the top. The precipitation as income value. We have the evapotranspiration on the top. Not only grass, like in this example, can grow. We have also lysometers with crops or even small trees. You have the runoff, and at the bottom you have the seepage water. These values now you are able to calculate very exactly the water balance for this part of the nature. We have different sizes of our lysometer technologies. The smallest one is our ready-to-go lysometer. You can see some pictures here. And we have this normally in different sizes, from around about 300 millimeter in diameter up to 800 millimeter. And from different depths, from 300 to 900 millimeter depths. All these lysometers, even the small one, are located on weighing platforms. And inside the soil column, we can customize, install sensors for measuring, for example, the soil moisture, the soil tension, the soil temperature, or even suction probes to excavate soil water. We have also bigger lysometers. You can see here some photos from our PHIDs lysometer stations. Our standard lysometer diameter is here. It's 1 to 2 square meters, and the maximum depth is around about 3 meters. Coming back to the weighing system, every lysometer is located. If we have a lysometer with with 1 square meter and 2 meter depth, the total weight is round about 5.5 tons. For this weight, we have a resolution with 100 gram and an accuracy to 10 gram. So if you imagine, if you have a rainfall for 1 millimeter, it means for 1 square meter that you have 1 liter. That means a weight increased of 1 kilogram. So, but the accuracy of 10 gram allows you to measure the dew fall in the morning or even the rim in the winter. For the lysometer technology, we have special sensor grommets. They are waterproof. They are available. You can see it here on this picture. They're available in every size for all the sensors we normally install. And it allows us to easy install and deinstall the sensors from the side. To get a natural temperature gradient in the soil column, we normally isolate the soil column from the side. So the aim is to get the same temperature profile in the soil column than in the outside. We have different methods to control the lower boundary conditions. This is a view from the down to 1 lysometer. So there are suction cups installed. With the suction cup, we are able to steer the tension on the bottom of the lysometer vessel. So if 1 tensiometer is installed outside and 1 is installed inside, we have the same tension in the same level inside and outside. For the temperature control, we install like a heat exchange system inside the lysometer and outside the lysometer. So then we have even the same temperature inside the lysometer than outside the lysometer. When you can remember, on the top we have the natural environment, the natural precipitation, the natural climate. On the side is isolated. On the bottom we have the tension like outside, the same tension and outside, and the same temperature like outside. So we have the total, or we try to simulate the total same conditions inside the lysometer than outside. So you can compare your results from inside the lysometer to the outside conditions to bring your results to the field. The first step of every lysometer is the excavation of the lysometer of the soil column. We have a patented technology to excavate soil columns in different size and lengths. They are guaranteed that the soil column inside has no fractions, that's not compromised, and that's the start of every lysometer investment. So another very helpful is that after the drilling, you have a horizontal. You see the horizontal layers of the soil and can investigate the horizontals, the layers horizontals, and then you know also what's inside the lysometer. The damage of the surrounding is minimized. You can see here a photo from Korea. We excavate there 55 lysometers. In addition to our lysometer stations with the tools inside the soil, we have also air chambers we can install on the top of the lysometer surface, or even not, or only on a normal surrounding. So with the chambers and, for example, the air samplers for soil, they can connect it to gas analyzers for concentrations or isotope measurement tools. Here's an example. We work together with the Caro, but we can combine them to every gas or isotope analyzers that our customers have. And the suction probe, and for example, the seepage water you can analyze with liquid water analyzers. By the way, we don't only have the classic lysometers, we have also roof lysometers where you can investigate the influence of green roofing for the climate of cities. We do not only have complete installations, we have developed special tensiometers, for example, for the installation in lysometers. Together with the University of Wageningen, we developed a patented full-range tensiometer, which is not filled with water like normal tensiometers. It's filled with a polymer, and the shrinking and swelling is measured by a pressure sensor. So it's a direct measurement for the tension up to 15 bar. So we always talk about the measuring the nature, that's for the lysometers, but we provide also for our customers the possibility to measure first the nature, then bring the monolith in our ecotrons and simulate the environment in the ecotrons, from the light to the air components, from the humidity, so you can the results, or you can investigate the global change under controlled conditions. Here is a photo from an installation we made by IDIF near Jena. So they built up 24 ecotrons with 4 lysometers each inside. It was a very short overview of our product range. So if you're interested, come back to me. We normally make it customized for everyone, and we try to make our customers happy. Thanks for your attention.
Dr. Hert, thank you very much.
Thank you.
The Agriphotonics CEO, Mr. Lior Hassel, will speak on a hydroponic greenhouse. Please.
I try to
clear the screen.
Yes. Thanks.
Okay, thanks. Lior, we are not hearing you. No, still. Switch on the microphone.
Okay, can you hear me now?
Yep.
All right. Sorry for that. Shall I share my screen?
Sure.
Okay.
Great.
So, agroponics. We build and we operate greenhouse factories. We have been doing it for a very long time in quite a few places around the world. We are we used to be high-tech engineers, but for many years we now call ourselves farmers, because we operate farms. We use a lot of innovation in our farms. We integrate greenhouse projects, different types of projects. Let me see if I do this. Is this better? Can you now see it?
Sure, it's better.
Okay, so we integrate different types of technologies, screening, fogging, heating systems. It all starts with finding the right location. It can be anywhere, even in the middle of the desert. We dig the holes, we put up the poles, we bring in the equipment, and we start building. We do the infrastructure, we build a factory. We actually build amazing factories, high-tech factories that have automation, special type of automation that we have developed. We do the pack house, we train the personnel, we do all the certification. This is a value proposition if somebody is interested, what would such a factory cost to install? But they're very expensive. They're expensive to build, they're expensive to operate, they're hydroponic. Because they're so expensive to build and to operate, actually the question is, why would you have to do it? You can actually continue working the land. There's no shortage of land. So what are the problems? So we have quite a few known problems. Transportation is a big problem. Logistics of food, pathogen, food safety, everybody knows. Labor, people don't want to work in the field in the open sun. There's water problems, both quality and quantity. And the industrialized washing of vegetables has not proven itself to be the solution. It's dangerous, it's expensive, there's food safety issues. So if you want to produce clean and close to the market, you need a greenhouse. If you want to do local production, you need a greenhouse. They're expensive to build and to operate. So for all of this investment, what you need to have is a very high yield per square meter. And how do we do it? We do it with two things. One is we use hydroponics, which is the most advanced growing system available today. And the second is use automation. And this is what I want to describe. Well, hydroponics, I don't think I need to describe. People know what hydroponics is. Very accurate injection of nutrients, very accurately into the growing solution. And then there's the automation. We've developed this very special automation system that allows to maximize the yield per square meter. We can do cucumbers, strawberries, tomatoes, other different types of vine crops like peppers and zucchinis and small melons and so on. What I wanted to present to you today is our new data collection robot, the DCR. You see, our greenhouses around the world are monitored by our control center, and we actually use the internet to manage our farms. And we have all of these sensors and even cameras, and we sense everything. We see a lot, but we don't see enough. If I want to take a tour in my greenhouse in New York, sitting in Haifa, Israel, I have a problem. And for that, we've developed this platform technology, which we call DCR, Data Collection Robot. The robot's purpose is actually to replace the human inspector and to collect the data and to analyze it. It's actually a platform technology which can be mounted with any payload that you would need. By the way, it can be used for other applications, like wherever you need inspection, wherever you need somebody to actually do a patrol and use his eyes and ears and collect data and report back. We Israelis know a bit about that from our security needs. But in the greenhouse, you also need to inspect, or in any farm, you actually need to inspect the farm and collect the data and then analyze it. And our method of analyzing the data is a patented algorithm whereby what we do is we actually compare. We compare and compare and compare. We compare what we saw today with what we saw yesterday and the day before and the month before and even the season before. And we compare a lot of things, but simple things like the percentage of green, or the percentage of brown. In our case, the percentage of white, because our trays are white in hydroponics. And by preparing these very, very simple parameters, we can conclude, we can analyze and find out if we have a problem, if we have something that we need to set or resolve. In order to collect this data, we needed something that didn't exist. We needed a camera that would be able to take the same picture from the same angle with very, very high accuracy, but more importantly, with high repeatability. And this is exactly what our system is actually doing. The system actually has presets, and it can grab a frame very accurately. The mechanics is quite accurate, and after the mechanics, we do the frame grabbing with very simple software that is, I could say, almost off the shelf. And we can actually have the same frame every day or every week or every hour if we wanted, and just compare. Just compare and see what changed from the previous picture. And from there, we draw our conclusions. So I can explain, I wouldn't want to explain the algorithm here, but it's all about deriving and looking for the changes from what we had seen in previous pictures. And mind you, it doesn't need to be only pictures. It can also be sound. It can be in the UV range. It can be in the IR range. But sounds, for example, are very interesting because as an expert greenhouse inspector, I inspect greenhouses and farms in general all the time. And if I inspect a farm that I already know, without even knowing why, I can sometimes know that there is a problem, just because the sounds at a certain area are not familiar. Maybe the pump is clogged. Maybe the filter needs to be cleaned. Maybe one of the panels flew off the roof and the wind is making a different noise. Just by the difference in the sounds, I can know that there is a problem. That can be done by a robot a lot more efficiently than even me with my 20 years experience inspecting farms. Thank you. If there are any questions, I would be happy to hear. I can also forward this presentation to anybody if there is a request.
Thank you very much. Thank you very much, Leo. I'm sure that people will be in contact with you. Is the University of Colorado scientist, Dr. Yin, is available? Probably not. Okay, so we will go to the last lecture by Archer Optics expert, Miss Lorraine and Mr. Squares. They will speak on spectral remote sensing optical. Please.
Hi, thank you very much for the opportunity to participate in this. It's as a Texan, I'm very familiar with the importance of this agriculture part of photonics. So we're excited to see all the progress that's been made in this area. So I'm going to go ahead and share my screen. Share.
Yes, we see it.
Okay. Okay, so we're going to talk about the optical hardware challenges for spectral remote sensing. This presentation will discuss the challenges with developing these imagers and some solutions that Archer Optics is able to provide for those challenges. As a note, throughout this presentation, agriphotonic imaging is assumed to mean remote imaging via drone. I'm going to give a brief overview about Archer Optics and our capabilities, and then I will hand it over to David, the expert on this topic. So we specialize in the manufacture of ultra-high precision optics and optical assemblies. We're located in Dallas, Texas. We're a small company of 34 employees. We're highly automated. So it's mostly electricity. Luckily, cost of living, electricity, taxes are all very inexpensive in Texas, so that helps us be able to compete globally. So we're able to bring you the highest precision optical components and assemblies cost effectively. So we focus on offering complete solutions to support each customer's needs. We're fully committed to bringing the highest quality, cost-effective products and services to all customers. We do this through service, personal expertise, and software. We're responsive. We offer on-time delivery and full technical support for all of our products. And then we work together as a team to provide you the most cost-effective product using our various manufacturing techniques. We use software, and we also have several engineers that specialize in different areas of the optical, mechanical, and systems engineering. Brief overview, we are known worldwide as the highest precision molded glass aspheric lens manufacturer. We also machine high precision A-spheres, A-cylinders. We do a lot of traditional components. And so we're able to use our advanced lens element manufacturing processes to bring you cost-effective, high precision lens assemblies. We also guarantee what we make. We have the highest, the largest metrology suite in the world. We guarantee everything to the final approved drawing. Our lenses go through a testing process that throughout the production so that everything meets its requirement. We can provide a COC upon request. If you want any data from metrology, we can provide that to you. We just need to know beforehand. Inspection is per your requirement, AQL, FAI, 100% pass, fail, etc. Also, any bench inspection is done with more Bluetooth precision gauges. Our goal is to make sure that we try to eliminate as much human error as possible. And I'm going to go ahead and hand it over to David. David?
Oh, hello, can you hear me?
Yes.
Okay, perfect. So when we talk about multispectral imaging, we are the people that deliver the lens and the lens assembly. So most of our customers do their own upfront, all of our customers do their own upfront work themselves. And so they get a complete, typically they'll get a complete data set from a hyperspectral imager. But then when they want to deploy this commercially, it can be a challenge due to the size and weight and cost of a hyperspectral imager. Also, the resolution is much lower than we can achieve with other sensors. And they also generate a lot of data. The amount of data that they throw off is difficult to deal with if you want to, say, inspect a field and turn that information over immediately. Next slide. Okay. Okay, so therefore our customers come to us and generally want to put a set of dedicated cameras on a drone, and because they want size and weight directly impacts flight time, which directly impacts the amount of coverage you can get in a field. Our challenge is always to get the imaging system down as small as possible. And we can actually go lower than 10 grams, but that can get fairly expensive and require a lot of investment up front. When we talk about 10 grams, that's the lens, the housing, the sensor, and the electronics. Okay, so as I said earlier, we don't develop the algorithms or the software. Our job is to provide the best image possible to work that magic on. So when I say best image, we mean high resolution, distortion free, in other words, geometrically accurate and spectrally accurate. And this is where we specialize. So typically our customers have to assemble a complete image from a series of tiles, and we call this stitching. So here you have, I like using images of cornrows because they show errors very well. So here we have picture of corn in a field, and typically a drone will collect a series of tiles like this on the right-hand side. However, lenses always come with some errors in them. So we have typically the two distortions that we're working with are barrel distortion on the top and pincushion distortion on the bottom, because they're shaped like barrels and pincushions, respectively. And here's what it does to an image if you're looking at, again, rows of corn. And so typically some level of software is going to be required to straighten these out. And in addition to some distortion, you might have pointing errors and magnification differences, and you end up with a variety of errors that need correction before you can paste together a full field worth of data from a drone that's flying around and sampling areas of the field. Typically, if it gets, obviously I exaggerated here a little bit, if it gets this bad, when you're done manipulating the data to get full coverage, you've created some new problems for yourself, because as you stretch and pull these images, you're changing your resolution across the different fields of view, and you're not sampling the field at the rate at which you really want it to be sampled. So our job is so that our customers don't have to deal with images like this. So typically our customers will have a series of spectral bands that they want to analyze. So they've predetermined what's important to them, and they will have some bandpass filters on dedicated cameras. And there might typically not as many channels as shown here. They might have 4 or 5 different spectral bands that they're interested in. Now these bandpass filters work as, and it's not important that you understand the physics here, but it is important that you understand the effect. They work based on the distance that each layer in the coatings on the filters have at different wavelengths. So they work on constructive and destructive interference, and they're designed to be a multiple of the wavelength that they're designed to filter. So next slide. But if you go in off axis to one of these filters, now all of a sudden there's a different path length in each one of the layers, and you're filtering a different portion of the spectrum than you thought you were when you had light going straight through the filter. So you end up with a filter that's shifted in wavelength.
Sorry.
So here's a picture. This is from a filter manufacturer, Semrock. Here's a picture of typically what happens with filters versus angle of incidence. The dark bandpass all the way to the right is what happens if you're going straight through that filter, and successively that moves to the left as this is shown as relative wavelength. So you're getting approximately 94% of, or you've lost 6% of your band if you are going through at 45 degrees. And here's another from a different manufacturer. Here's a specific filter that starts out filtering at about 1060 nanometers. And as you go successively off axis, you end up selecting, instead of 1050, you're now at 1020. So by using one of these filters with an off-the-shelf lens, you can think you're seeing a part of the spectrum that you're not. And here you can see an example of that. This is just a generic lens that I've laid out here. And if the piece of glass over on the right-hand side is your filter, you'll see one spectrum in the center of the field of view. And as you go off axis and the rays go through the filter at a steeper and steeper angle, you will see a different spectrum going through the edge of the filter. So we've developed a series of lenses specifically for spectral remote sensing. And here, this is a typical lens. The filter that I'm pointing to over on the right has all the rays for the different parts of the image field, going through it all at the same angle and all going through it perpendicularly. So if you've, whatever band pass you've selected for your filter, you are seeing exactly that band all the way across your field of view. And this actually has a pretty good field of view to it. That was at least 60 degrees. So when people choose catalog lenses, and I'm not referring to our catalog lenses, but just a typical, you know, what you can get off out of any optical catalog. It's a quick, cheap way to get a camera in the air and start doing some sensing. But when we pair them with a filter to start selecting different parts of the spectrum, you start seeing anomalies, spectral anomalies that are not related to the data you're looking at, but are related to the optical system. And typically they will have some distortion built into them, and typically there's also magnification changes that can happen over the different spectral bands because they're not designed to do this. And then you need a lot of software manipulation in order to line those images up correctly. And then you end up having changing your apparent resolution when you do that.
Okay, so we do have some off-the-shelf, what we call the SIVA series, which stands for System Imaging Vision Assembly. So we use our expertise in ultra-high precision lens manufacturing to bring you the perfect lens SIVA series. These are specifically designed for spectral remote sensing. We offer off-the-shelf high-res wide angle, high-res standard angle, and high-res narrow angle. When I say high resolution, we offer 250 or 300 line pair per millimeter for a 15 megapixel sensor. The field of view for the wide angle is 70 degrees. The narrow angle is 10 degrees. And then the standard is 36 degrees. We also offer 225 line pair per millimeter for a 5 megapixel sensor. So we have some options available off the shelf that could be a cost-effective solution for you. Okay, David. Also, sorry, the slide's missing. The custom, we also offer a lot of options for custom when these off-the-shelf do not work for you. These are designed with our engineering and production to function very near the computer design model. And we are able to work together to make these cost effective for you.
Okay, so another, somebody's asking about chalcogenide. Yes, the answer is yes. We do work with chalcogenide.
We actually can mold and machine the chalcogenide as well.
So another challenge, yeah, okay. So another challenge with using catalog off-the-shelf lenses is in the near infrared, since catalog lenses are always designed to be used in the visible spectrum. They will make an image in the near IR. Most of our agricultural customers always want information in the near IR, and while the catalog lenses will work there, the resolution is going to be compromised because when they were designed and manufactured, no consideration was given to how they perform out, say, at 1,000 nanometers or 1,200 nanometers. And there's always going to be a magnification change out there too. Mike Richardson has some experience with that, I see. Okay.
Please.
There's my custom SIVA. Okay.
So here's just a summary of one of our lenses. Again, this is just a repeat of the previous slide. We always make sure that we have a spectral filter that's actually doing its job across the full image field. Here's a typical lens showing the distortion. The grid you see there is a perfect lens. It's where everything should be, and the little blue X's that you see are where this particular lens actually delivers. So there's a little bit of distortion out in the extreme corners, but generally not much. And for this particular lens that I chose to show here, the difference in magnification over 5 spectral bands is less than 13 microns. And when you're tiling images, you always overlap a little bit anyway. So the 13 microns is insignificant to our customers. Here's MTF. This is what Janelle was speaking about earlier. This is basically, if you're unfamiliar with this graph, it's basically resolution. The vertical axis is contrast, and the horizontal axis is spatial frequency. As you move to the right, you're looking at smaller and smaller objects. And this goes out to 200 line pairs per millimeter, and you're still getting really good contrast there. And this is the same lens in the near IR, just showing that, so we've extended its spectral capability out so that if you are sampling in the near IR and you've put some bandpass filters out there, you're still going to get very high resolution imaging.
Sorry, but we have to conclude.
Okay.
Yep, we are done.
This is our end. So thank you again for the opportunity to participate in this. As I mentioned earlier, we're very intimate in the importance of agriphotonics. So we are happy to assist you with any needs you may have with your spectral imaging. Thank you.
Right. Thank you to Miss Lorraine and Mr. We come to the end. So I would like to thank all the speakers for their participation at the conference. I wish you all success in your advanced agriculture activities. I hope that this event has served as a start point for further collaboration. I thank Optech Berlin-Brandenburg, Vulcani Research Center, the staff of Israel Engineering Association, especially Mr. Roy Lezerovich for organization of this valuable event. Conference recording will be available shortly after we will receive the speaker's permission. Looking forward to see you all in October at the Photonics Days organized by Optech Berlin-Brandenburg. Thank you very much.
Thank you very much, Shlomo.
Thank you all. Thank you.
Thank you very
all.
much.
Thank you all. It's been a pleasure.
Thank you.
Thanks, everyone.
Thank you very much.
Thank you very much. Have a wonderful evening or day wherever you are. And here's
Mike, thank you very much for the warm words.
Oh man, it's so awesome working with you, Oded. I mean, that spectral index, we can't give away too many details, but I keep looking at it. It's magical. I just keep tuning the spectral sensor based on that data. Ooh.
Thank you very much. Okay. Thank you, and Shlomo, thank you very much. Goodbye.
Thank you.
Bye-bye.